Thank you, Dr. Charu. Good morning to all of you. Today we are in the last day of the seminar, short course on satellite meteorology application in weather and climate studies. And in this session, we will be learning more about the detection of trace gases from satellite. First of all, I am thankful to Dr. Charu, his course coordinator, who has given this opportunity to share my views with you. Mostly in this session of 1 hour, we'll be discussing that how these trace gases or greenhouse gases are detected from satellite, what are the various methods, what is the state of our technology today, and how they are varying, and different applications of that observations. So I move forward, and in the background, that why we anyway know or detect about the greenhouse gases is the fact that we all know that Earth climate is changing. With what rate are the causes natural or human use? What will be the climate in future? It remains a challenging question. We have few answers with us, but then the question continues because the accurate measurement of these greenhouse gases from space help in answering that with what rate things are changing. You all know the Mauna Loa observations of CO2. That is one of the very good observations which shows that how CO2 is changing. But that is a point observation. Therefore, a few more observations taken in different parts of the globe. But then measuring from satellite tells you the global picture of how these gases are changing. Not only the CO2, the CH4, ozone, and many of these gases. Of course, the technology of detecting these gases from space is a important area. And the last few decades, what we are seeing is that not many good satellites has come up, and this technology of spectroscopic detection is improving day by day. So in this session, we will learn that what is the technology available, how people are doing it, and all these things. So the talks will cover about satellite remote sensing and its role in providing the variable observation related to these greenhouse gases. I'll be more focusing on CO2, CH4, as it has been my area of experience while working in this field. So ultimately, what we are going to discuss is the need of detection. Why should detect? The basic and global missions, instrument concept. Slightly we'll go to the instruments, kind of instrument are used in doing that. Physical principles. Retrieval, how do we retrieve or estimate it? Some interesting finding, and the future direction, how this particular field we have to go ahead. So you all know the basis of life on Earth is all, there's a beautiful cycle of water, the carbon, balance of energy. Everything dictates this planet to be a habitable planet. And carbon cycle is one of the important cycle which dictate the various aspects of biogeochemistry. And we also know we have a huge amount of carbon stored in atmosphere, the land surfaces in the form of vegetation and those things. And even more, much more carbon is there in the ocean, particularly deep ocean. So one is that how much amount we have, and second, that what we call is the reservoir of carbon. Okay? And second is how they exchange among each other, like how atmosphere exchanges carbon with the vegetation, how ocean exchanges, and there is a circulation, continuous exchange process. It is going from thousands of millions years ago. But the whole problem or situation arises after 1750, what we call industrial era, where we started releasing much more carbon, digging our earth surfaces in form of fossil fuel or changing our land cover patterns. There comes a kind of disbalance that we are producing more carbon and they are not getting again synced into. So cycle is slightly disbalanced. So exactly what is happening? And if the cycle is not properly maintained, or there is excess of carbon going into the atmosphere, obviously atmosphere, when become carbon rich, CO2 rich, it will absorb in near infrared region and create global warming. And that's why we are seeing with the time this warming is happening. And this has been a phenomenon after industrial phase. So to find a solution that it should not happen, because if we are much more warmer than what we are, it is not good. We are colder than what we are, it is also not good. So a environment or atmospheric condition defines the habitability of a planet or system. So Earth is the only planet what by now we know is habitable. It is all because of the composition of gases and the atmospheric processes. These atmospheric gases are not bad. They are not enemy of us. They are required. They are required to maintain the temperature what we have. Only their composition, if you increase beyond a point, then obviously it will create another issues. And one of the issues is the warming. So what we are seeing, because of fossil fuel burning and somewhere the land use changes, like we are cutting forests, making agriculture, these changes or more urbanization is pumping more carbon dioxide into atmosphere. Generally, 2 ppm or slightly more than that, atmosphere is CO2 is going into the atmosphere. So that we have to monitor and take appropriate measure to control it. So let's see what is happening. What our Mauna Loa and many ground observers suggest us, they are suggesting from 1850 onwards, things are increasing gradually and gradually, and not only one gas, even CO2, CH4, N2O, because if you increase the pollution or things, it happens in other gases, many gases. And it has also been analyzed now by now, it's quite clear that a major contributor is fossil fuel, cement and all those things. And of course, forestry and their land use is also an important one. But in the relationship to each other, fossil fuel is a much more important. And that has to be controlled. So as I said, when these gases are increasing in the atmosphere, obviously they are giving warming. And if you talk about in 1951 to 2010 sort of contribution, it has gone to 0.6, 0.7, in which greenhouse gas is a major contribution. In fact, the contribution of greenhouse gas would have been much more, but there are some counterbalances from the aerosols and other anthropogenic factors, which also cool us. There is cooling effects from the aerosol and scattering processes. So in the net, we have a balance, but this balance is also increasing day by day. So what we have to do, we have to monitor them. We have to see them accurately. So one of the technique is remote sensing technique. In today's session, we'll be talking about more about this technique. Although there are various measures of ground instrumentation, they also do it very accurately. Only limitation there is that you cannot have many networks of that nature. So remote sensing, for those who are new to this subject, is a science of making inference about material object from measurement made at distance without coming to physical contact with the object. So when you see something from a distance, an observer, not only see, you observe, measure, and know its property, particularly for Earth features like surface, atmosphere, ocean, we call Earth observation and remote sensing. You require various instrumentation to do that. One instrument is called hyperspectral spectrometer, LIDAR, passive radiometers, radar. So various kind of instrumentations are used. This picture shown here to you is a fleet of satellite which generally go around 115 to 130 PM every day. We call atmospheric train. All the satellites have the unique instrumentation in them. Today I will not be discussing in details about it, but I'll be talking about what are those instruments which are related to greenhouse gases. Particularly, you can see OCO2 there in the right-hand side. It is an instrument called Ocean Carbon Observatory. So it has the ability to detect the CO2 gas. Similarly, few more satellites are there. We'll be talking in details how they do and what are those satellites. Generally, when you do remote sensing from space, obviously, most of the time we look Nadir, just below to us. But for when we look below to Earth, we get a reflection from surface. So that is one technique of doing. So if I know my properties of surface, I can know the property of intervening atmosphere. But many a time, if I have to detect ppb or ppm levels, many times surface contributions are not required. So what you do, you start seeing into a inclined way so that you do not get reflection for surface, only see the atmospheric component. That inclined viewing is called limb viewing, where from a satellite you only look at atmosphere and see its emission. This technique is good technique. I'll be talking details about later on. And there is another technique called sun or moon occultation. You directly see the sun or the moon where intervening atmosphere comes, but no earth or surfaces come into picture. So it is some sort of variant of limb, but there you see a source occulted, a sun or moon. Broadly, talking about the physics of this process is generally one looks either in optical region, one looks in thermal infrared region, one looks in millimeter microwave region. These are the electromagnetic spectrum in which observations are designed, applied. So if you look in optical region, obviously what you are going to see is a solar reflection from the surface and use those properties to detect. If you are working in thermal region, you don't see reflection because there is no, generally it is done in night, you can do in sun also, but there you want, the day also, but there what you work is see the emission part of the object like Earth, not the reflection, okay? And third, as I said, is millimeter or microwave. This also, one does take an emission part of it, and while working in either the reflection or emission part in thermal and infrared, what one does, one looks into a very detailed fashion in spectroscopy sense, like the wavelength in which, the wavelength band which you see is very, very small, many times nanometer, less than nanometer. This kind of technique is called hyperfine resolution spectroscopy. It is not that you look into broader wavelength. For many of the other cameras, they work like that. What you see into a very fine spectral channels. So you choose a filter of that nature. And if you start seeing in those specific wavelengths, like I have given you some numbers, CO2 7.2, 14.99, 4.25, CH4 I have written here, 3.42, 6.51, 3.31. 3.31 is a very important micrometer range of CO4 detection, 7.65. So there are many numbers. They are already known through spectroscopic analysis. If I focus my camera or a spectrometer and split the lights into this smaller channel, around this, I start seeing the contribution of these gases. That is the basic principle. There is a principle of gas correlation also. There we have some gas cells into it, and from there you try to detect, and that is put into a MOPIT instrument, and that works in the infrared region. So essentially, using all this technique, there are some sensors, I will just name it for you. They are CMIT, GOSAT, OCO2 I was talking about, TROPOMI. They all work in the reflection domain of optical region. Thermal infrared, there is TES, IIRS, and few more are there which works in thermal infrared. MOPIT is an instrument which detects CO and CO4, but that works with the principle of gas correlation spectroscopy. And you can also see a lot of gases in millimeter wave or microwave. And one of the important instruments is MLS. It works from 118 gigahertz to 2.5 terahertz. This is called terahertz technology. There also many of the gases are possible. We'll slowly go into details of some of them. Of course, we may not go in details of all. So let's see that how they work. But just remember, I'll just summarize. While detecting gases, you choose spectral regions, either optical, thermal, microwave. You choose because of interest of a gas you have in your mind, which gas you are detecting. Then you do some kind of spectroscopic analysis. There are various instrumentation made in this region, and they are targeting a specific gas. So how this particular trace gas detection is different from a conventional remote sensing? Those who are knowing this conventional remote sensing may be aware that we have our IRS series, resource sat, INSAT, and many satellites are there, Sentinel, Landsat. Can they detect trace gases, CO2, CH4? Obviously not. Why? Then what is extra about it? So for those who are new, I would like to say that our it is mostly the spectral resolution, the ability to detect the spectral purity or the width of the what called wavelength in your detection. If it is a broadband, like a visible sphere or 70 to 80 nanometer, generally our most of satellites which do terrestrial remote sensing are 70, 80, 100 nanometer satellites. You can estimate albedo. You can do some NDVI and resource management. They're good for that. But if at all you want to see finer details of any surface or atmosphere, you have to go to hyperspectral domain. In this domain, what happens? Generally, in the normal broadband multispectral, you have 3, 4, 5, 6 kind of channels in your sensor. But if you go to hyperspectral domain, where your ability to resolve the wavelength is 10 nanometer or 5 nanometer, then you have generally hundreds of bands with you, 100 or sometimes 400. But there you can detect mineral, pigments. You can even detect the type of the what you call stresses into a plant. But these sensors are also not good to detect the trace gases because they work in the order of 10 nanometer spectral resolution or so. To detect trace gases, you require much finer resolutions, a 1 or 2 nanometer, or even better than that. And those instruments are called advanced hyperspectral instrumentation. And do you know, there are thousands of channels, 7,000, 8,000 channels in those particular instrumentation in a given window of range, which part they decide or they design. And there you start seeing the fingerprinting of those molecules because molecule transitions are they are line transitions, they are not broadband transitions. And those line transition bandwidth are smaller. So this gas instruments we detect gases or technique to detect gases is a specialized branch of remote sensing. That is why it is not done by generally traditional remote sensing sensors. Now, we have many sensors interactions also for tropospheric composition from space. And they are TOMS, GOM, MOPIT, CMACI, MIPA, SAYS, TES, OMI, MLS, OCO2, GOSAT, Sentinel, TROPOMI. These are the broad names. You can see here the launch date. They started from 1979 itself. The TOM instrument was designed to see the ozone hole in the poles, and that was a discovery done in those times because people are not aware about how ozone is depleting. And there onward, the GOM and then OMI, and there's a series of continuous satellites are going on, which has a constant visit on how ozone is changing because it was one of the environmental concerns. At the same time, there were new other sensors also developed in this line. And at the moment, there are many trace gases, ozone, CO, CO2, NO, NO2, HNO3, CH4 methane, SCHO, SO2, BRO, and all these kind of things can be detected from satellite, and they are being detected. My purpose of this particular short course and today's talk is to make you aware about the canvas of the literature available, the data sets available in this direction, so that anybody planning any particular activity can further deal and go and study these facts. If you talk about the current, I'll just now focus upon some instrumentations. Of course, they are big lists, so I have to focus somewhere. I would say that many important trace gases which works in UV visible NIR. I'm slightly focusing into the optical regime. So, as I said, they are GOM. They have mostly FTR, that kind of spatial resolution. Most important in direction for CO2 CH4 was CMAKI, which was launched in 2012 and worked for a decade around so. But the resolution was around 30 kilometers. Then the advanced version of CMAKI is TROPOMI. At moment, which was launched in 2017, it has 7-kilometer resolution. It works in 270 nanometer to 2385 nanometer, roughly covering all the visible, the NIR and UV radiation. And swath is quite good. It is around 2,600, a big swath. So for those interested in CO2, CH4 and those gases, TOPOMI is one of the best instrument at the moment. And those who are interested in continuing your study in ozone and those aspects of it, OMI, ozone monitoring instrument, is one of the very good instruments. Although ozone can also be detected from this TOPOMI, other satellites. This whole story of CO2 started with a paper where they first time detected from infrared sounder, which was not made for this. If you do sounding, sounding means knowing the temperature, humidity profile, and vertical levels. One uses the CO2 absorption band around 14 micrometer, and there you believe that it is well mixed, so all the temperature estimations are done by that. But a team started working on it, and they found there are some uncertainty in the measurements because of assumption of CO2 being homogeneously mixed and constant. Or when they inverted the problem, knowing temperature humidity well, they could compute the carbon dioxide from high resolution infrared sounder. And there started the measurement of CO2 from space, and a lot of observation from that came out. And by the time there was few instrumentation, IMG, it is interferometer by NASA, IIRS, AISI, IC, CRIS, these are instruments available. They have this kind of infrared sounding unit into them. So they do sounding in infrared region. And they become now a very important source of not only meteorological application, knowing the vertical distribution of meteorological fields, they also are good in knowing the trace gas compositions. This is one example where I was working through an instrument called tropospheric emission spectrometer. So if you see the spectrum over land or ocean, you start seeing the dips and all those things into the spectrum. And there lies the absorption of these gases of O3, CH4, HNO3, CO2. So what one does is and observe the data from satellite. At the same time, you should have an ability to model the spectrum at different compositions and atmospheric conditions through a model. Here we use Motron model, but there are many other kind of RT model exist, and go on simulating the pattern similar to that, and then retrieve that this must be the atmospheric composition of that particular day. So spectrum looks like this. This all spectrum lies in near infrared region. But let's talk about if you have to do CO2 and CH4, I generally prefer work or have seen that optical regime is important regime because you get more light into this. You have a source, sun acts as a source. In infrared region, what happens? Only you have to see the Earth emission, and that signals are feeble. So what will happen? Your resolution becomes coarser. If you work in an optical regime where already sunlight is falling on Earth and going back and detecting, you have a good SNR, signal to noise ratio. So spatial resolution and detectability becomes high. Not only that, you start seeing near surface processes because the reflections come from the ground. If you work in infrared region, many times your observations are above the surface of mid-troposphere and others. So depending on your application area, both are good instrumentation. But in fact, you are going for the optical regime CO2 CH4. The good example of at moment is NVSat CMAKI, but it is not functioning now. We will get a decade data from that. good amount of data, but is not functioning now. GoSat is a good instrument from JAXA. It's called greenhouse gas satellite. It has a Fourier transform. I'll just be talking about a concept. NASA OCO2 is a very good instrument. I was telling you about CO2, and at moment, as I was talking about Sentinel 5P tropomi. So how they do it internally, instrument sense point of view, say. I mean, they have obviously instrument has a telescope to gather the light, then it has a slit to collect the light into a line fashion, and then you have a dichromatic, which what you call a collection of light takes place for optics, and then when it goes from a collimator, a grating is there or some other dispersive device which splitted the light into different components, and later on that splitted light of different wavelengths are imagined over a CCD detector in different way, and detecting them into a CCD and reading them gets you a spectral response at different wavelength. Now, the resolution of your instrument depends on the kind of grating or dispersing device you have and the requirement of a particular gas. Now, for disperse, you can have a grating. Grating, you know, is a sort of a glass where you have a lot of lines into it. Even many times CD also is a grating. When you see colors in CD, it all happens because it has a line and you see beautiful colors. So, but for this purpose, specialized gratings are used, which split light into different components. Many times, if you have to resolve much more than certain resolution, spectral resolution, one uses a FTIR concept. What is FTIR? Fourier transform infrared spectrometer. It is based upon a fact of a principle of Michelson interferometer. Those of you who belong to physics background can appreciate that you might have studied in your school or college time that whenever you pass a light through a beam splitter and half go to one mirror and half go to another mirror, when the light from the two mirrors again get combined, they give interference pattern. This constructive and destructive interference, and this interference is a function of wavelength and the displacement of the mirror. Looking at this configuration, you can create different wavelength pattern. So you can split light into desired wavelength resolution. This is one of such concept. Later on, whatever you split through Michelson interferometer, one does some signal processing of Fourier transform to separate out those signals of different wavelength, and there you are able to detect the spectral signature. So this concept is called FTIR. It is slightly evolved concept, so there are less instrumental based on this. But when you want to detect a very lower feeble concentration in PPBs and all those things, such concepts are required. GoSat is a FTIR I was talking about, while Siamaki OCO2 bases its principle from the grating principles. So what we do? Ultimately, when you start worrying that I want to study this gas, so you choose a first of all gas of your interest. Do you want to study CO2? Do you want to study methane? Do you want to study NO2? That depends on the scientific problem. Now, once you choose a gas, like I want to study NO2, I want to study CO2, then you choose certain spectral regions. Already by now, from physics principle, the regions are known, that these gases are known to absorb into various spectral regions. Now, looking at the spectral windows, I am showing in front of you that O3, O2, H2O, CO2, broad spectral windows are shown to you. One chooses this spectral window to design a spectrometer. Okay? I'm just showing a small simulation that if you see the wavelength region from 1.51 to 1.71, okay, this is a spectral window in which CO2 and CH4 are detected. So once we were doing a simulation, if you take all molecules, they will give you the first top of the what you call it, graph, where you see a lot of zigzag. I mean, many of them are having their influences. If you take H2, it has its own influence. If you talk about CO2, then it has a specific absorption at 1.57 and 1.61. this OCO2 use this particular concept. They choose this particular window and they are working on this principle so that they can detect CO2. So this is one of the windows they detected. But remember, when you see all molecule as 2 CO2, so you see different spectral patterns. When you detect them a spectrometer, obviously spectrometer detect all the contribution from S2 and other molecules. Then, depending on the modeling exercises, one has to separate out the contribution of others to detect a gas of interest. Then how much spectral window or resolution is required is one of the fundamental questions if you are a designer of the instrumentation. If you are a user of this data, you should not worry about it. Because anyway, the data will be provided to you. But if you have to design an instrument, you have to worry. So what we did was we did small simulations in different spectral resolution, 0.025 nanometer, 0.15, 0.25, 0.4, 0.5, and see that how the signals will look like into, at least in CO2, CH4 domain I was talking, 1.5 to 1.7 micrometer region. So many times you see extra information that is also not required, because to do that you require a very costly and high sophisticated instrumentation. You have to see that you should not have a very less information into it, because everything is averaged out. So obviously you are not going to detect. So there is optimum requirement. What we could find that during our analysis for CO2, if we have 0.2 sort of resolution, it makes good optimization that we can detect CO2. During our study, we found out. Similarly, you can do for what we did for CH4 also. You choose those windows, do the simulations, average out those wavelengths, and go and seeing it. So essentially, we found that if you are range of 0.2, you get sufficient signal, and instrument also has the ability to split light into it. So generally, that's how the current designs of spectrometer goes into this particular range. So this what you call instrument, just for sake of background showing you, it was a very good instrument. It gives a new dimension to this gases measurement, and later on many other instruments are being updated or advanced version of the basic concept what CMAK has. CMAK started from UV region only. 240 nanometer it had 309 nanometer, then it has 604 and round, then even it had sphere and all those things. And you can see they decided to have their FWHM, they call, when you define the spectral resolution of a sensor, how do you define? Full width at half maxima. If you take any response in a given wavelength, you will see that there is a Gaussian sort of system, that in some wavelength region you get high response, nearby system you do not get good response. So what you have to worry about, you have to see a full width at the half maxima where response was half. That defined the spectral resolution of the instrumentation. And so I have, you can see from here, they detected mostly, they designed most of the instrument in 0.2 or 0.5, this kind of ranges. So that is why it again proves the concept that our conventional instrumentation, like Landsat, Sentinel, those who are aware, they are 70, 80 nanometer, wide. Even our current hyperspectral instrumentation, like IIRS and many other instrumentation, they are of 10 nanometer wide. But to do trace gases, what you require is around 0.2, even less than 1/5 of the nanometer. And there comes the what you call challenge in making it. But then gases exhibit their, their spectral signature or their property into so narrow width. Why? We'll be discussing sometime later. So it's another example of another very good instrumentation currently working, that is called orbiting carbon observatory. Those who are interested in taking CO2 observations any place in the globe, you can always take it. It's a NASA instrument, very good instrument. It takes observation at 10 kilometers. Even they have a capability to work at 1 kilometer. Sometimes they take observation 1 kilometer. In right image, you can see they published a paper in Science in 2017 about this development of the technology and its application. And in Los Angeles Basin, you can see they could detect the variation of carbon dioxide. Okay, what is the basic design? They work in 3 spectral window. One is 0.76 or so, which is a oxygen spectral window. So they have to detect oxygen because oxygen is more dominant gas. To know the air pressure, you need to know one composition of a very dominant gas. Then only you can know atmospheric pressure. In detecting all these gases, atmospheric knowledge is required. So they work first in 0.76 and detect the composition of oxygen and that related to atmospheric pressure. They also work in 1.5 to 1.7, which I was showing you earlier. And then they also have another window called 2.05 to 2.7. This is more suited to CH4 window. So in 3 windows using this radio transmission calculations, they are able to tell you about the CO2. Yeah, the 2.05 window is also for CO2. People use for CH4 and CO2 both. Both gases has a contribution there. Here they use this window for CO2 detection. This was the first spectroscopic observation. They call first light from OCO2. They got it. You can see a typical laboratory sort of signature that you start black. You see black and white lines. Why they are black and white lines? Because in those black regions you do not see much light because the particular gas has absorbed the light. And this the black line is of the order of 1/10, 1/5 of the nanometer. That is why you require a high spectral resolution. Let's talk a bit about Sentinel-5 Propomi. As I said, it is one of the best instruments at the moment, and it is generic in nature, and it has a advanced version of CMIK. It is an improvement of CMIK in many respects, and one of the good things is that its swath is very good, 2,000 kilometers. So it's cover India or that of country in a major portion of India at a time. And good thing is that its resolution is 7 kilometers. CMIK was 30 kilometer and even OCO2 is 10 kilometer. So it's one of the best resolution by now. And why resolutions are coarser in this region? It is only because in this, when you do smaller what called delta lambda detection, obviously energy is smaller. So you have to integrate over a larger region. So one of the advantages of smaller delta lambda, the wavelength resolution is that you take gases, but energy also becomes smaller. So to try to see that your IFOV, the footprint in which you are getting the signal, is a large. Let's quickly go to another instrument called GOSAT. What I said, GOSAT is it is Japanese instrument. This also targets a similar way the OCO2 targets. The 0.76, they work for O2 kind of detection, 1.57 channel and 2.0 channel. But apart from that, they have an additional channel in thermal infrared. That is addition to what OCO2 has. That is why they are not targeting only carbon dioxide. OCO2 is targeting the carbon dioxide, where these people are targeting carbon dioxide and methane. So they have one additional channel in thermal infrared region. And the configuration is a Michael interferometer-based spectrometer, not the grating. And it is also a very good instrument. I have worked on this instrument. And those who are interested in studying the variations of CO2 or CH4 across the globe, it is very good to use this instrumentation. The spectrum you get out of this is like this. For a vegetated region, I was just studying. So I'm just showing you that if you have interest in analyzing this, such kind of patterns, raw counts come from them. Of course, if you are not interested in the raw counts of this nature and you don't want to go to the basics and retrieve any processes, then you can allow it to work on their products and use them for your applications. One thing here I would like to put you that there was an atmospheric spectrometer developed by Canada, and India launched it. So there are many small systems also people make it nowadays, and the scope of making such is quite good. I'm not going in details here. And just for sake of reference, let me tell you that in Mars orbiter mission, there was an instrument called methane sensor for Mars. This instrument also worked in 1.6 micrometer range I was talking about, which is good for CO2 and what you call methane. And they selectively choose those lines where methane absorbs. But here what they did, they neither use the grating, neither use the FTIR, because they are bulky instrumentation. In this case, a miniaturized instrumentation was required. So a concept called Fabry-Perot-Etalon. It is an optical device based on interference by which you can detect a smaller wavelength region of specific to your interest of region where this particular gas absorbs. That principle is used into this machine and this particular instrumentation. So we'll quickly come to the spectroscopy aspect of it, that how do we detect them? So obviously you know from the basic that whenever in astronomy, it is a very known principle that when you get a light, spectrographs which made up of this, either used to made up of great and long back the prism or the gratings, what you do, they start showing you some kind of absorption. First, it was detected by Fraunhofer, well-known example that Fraunhofer lines from the showing that absorption of various elements in the star started the basic spectroscopy. And now you know that all the library of different gases and elements are well known from the last 50, 60 years. In India, the Banaras Hindu University was one of the pioneer institutions, including IIT Kanpur and BARC, where the spectroscopy started first. And they were doing from, in 60s or 70s era, they have a field spectrographs where various molecules, the spectrums in emission or the transmission domain were that collected, and now similar kind of instrumentation are being put into the space instrument devices, satellites, and they are working. The principles are known from the laboratories. Now it has gone to space, and the basic philosophy of working or detecting is that the motion of two particles in space can be separated into translation, vibration, and rotational motions. So you all know if there is a molecular composition like CO2 or CH4, obviously it will have its vibration, rotation, translation. Now this vibration, rotation, translation will provide what you call different energy levels. If you talk harmonic vibrations, and since they are bonded, they will have different energy levels, and transition of this energy level define the wavelength in which this either emission will take place or absorption will take place. For example, if we talk about CO2 molecule, it has a symmetric stretching at 7.2 micrometer, asymmetric stretching at 4.26 micrometer, and a bending at 14.9 micrometer. And then combination of various what you call stretchings and bending provide different feature in electromagnetic domain. The prominent feature in near infrared 1.57, 1.66, 1.60, where I was talking about, is all because of combinations of this stretching and asymmetry and bending. Without going much into the spectroscopic knowledge that what wavelength, why molecule detect, is quite well understood subject. And if you take the different spectrum, like if you take a group of molecule or individual molecule, you will find them that they have absorption or typical spectral patterns in different wavelength region. That was to be understand that anybody who wants to design or work in this area has to know this problem. Let's now quickly go to the principle of detection. Now, if I have detected some absorption features or at different lambdas, so what? How do I know the gases concentration? Okay, that is the basic question. So the general principle lies with the fact that you, take help of Lambert-Beer law. What Lambert-Beer law says that if there is a source and there is an absorber of concentration C, when you detect, your intensity at given lambda will decrease exponentially. And the decrease is a function of what? Absorption cross-section of the molecule, the concentration of the molecule, and of course the path length in which our light would have progressed. Using the same principle, since we know the absorption cross-section from a spectroscopic measurement laboratory, we know the path length, we know the intensity initially coming there and the intensity in the detected fashion. What I can know? A concentration, which is nothing but log of the ratio of the intensity original upon the attenuated intensity upon the absorption cross section and the path length. So this is a broad principle, but if you start actually doing it, you'll find many variant about it, because it is not the only one particular gas which detect your signal. There are many gases, and not only the gases, there are aerosols and many other things which are giving you this signal. So an analyst has to do many complex radiative transfer modeling. The principle lies here is that, just I'm showing you a small simulation we carried out, that if I detect a signal in 1.5 to 1.6 region, what you see? You will find that as concentration increases, the signal become lesser and lesser in few absorption bands. So you see more dips. We have simulated at 200, 400, 600, 800,000 ppmVs of CO2 in this particular window of 1.56 to 1.62 micrometer. So you see, more the concentration, more the absorption. So if I'm able to know the line depth, how much absorption took place, we call CIBR technique, continuum interpolate band ratio, we can know the concentration of it. There's one simpler principle by which you can know. Let's quickly go to the various methods. As I said, there are backscatter, the emission, the occultation, LIDAR principles are there, even sondes, aircraft, satellite do all these things. I talked to you that some instrument like SAGE, POAM, GOMOS, they work on the UV and near infrared in terms of what you call limb observation. Limb observation, your large signal noise ratio. In this case, what you see, you don't see the Earth contribution. So ultimately, your accuracies were high, you get good signal. But same time, you have a limited coverages and resolutions are also poor. Backscatter is a very good example. I mean, where you start seeing the surface contribution as the atmosphere, energy is also quite good, and you see absorption and compute the concentration. But here also, I mean, issues come because you have to solve about the Earth's contribution. But good part is that it is sensitivity to lower troposphere, and you have a good spatial resolution. That's why such instruments are more popular. Emission, also you can work on it. In this case, an Earth emits and the intervening atmosphere absorbs something and you start observing them. In this case, it's quite versatile because many of these atmospheric gases, they exhibit their signature in near infrared region, thermal infrared region. So that way it is good. You can do vertical profiling also. But in this case, the signal to noise ratio is poor. Nowadays, people are working on the LIDAR principle also. And in future, at moment, LIDAR has worked for the aerosols, but in future, there are designs for the trace gases. And very soon, I mean, it may happen in a few years that there will be an instrument which is LIDAR-based instrument, which is designed for a particular spectral window. And I was listening that a methane instrument based on LIDAR is being worked out at 2.1 micrometer. So mathematically, it is a difficult problem that you have observation of spectral nature and you have to know what you call the concentration. So ultimately, what you do is pose a problem, have some a priori knowledge of that region. Obviously, you require to have some a priori knowledge, what was the temperature, humidity condition at that time, build a model into it, and go on doing iteration at the condition in which your observation and the model go on matching it. It's a very complex mathematical inverse problem, but people do it in this case because we have many observations. Here, the lambda of the observations are very high. So essentially, as we're talking about, you have a satellite observation, you have a RT model, and you have a temperature, humidity, and a priori concentration. All mix up a priori model with a priori knowledge, go on running, see where this matches take place, and then do a inversion process, make the guesses, and come out with those concentrations. OCO not only works in this only knowing the concentration, they are transport chemistry models by which even you can know the source and sinks of the region. But what I do if I only know the CO2 and methane, there is one particular thing. By their variation, even I can know whether the particular process there is sink of CO2 or emission of CO2. For that, you require another atmospheric transport chemistry models. So let's go quickly to some of the examples because we have got now only, I think, 5 to 10 minutes to, yeah, it is 53. So we have got few 10 minutes with us. So let me show you, it was a very nice breakthrough from OCO2 in science. Even the cover page was showing you that you can see that CO2 variations now. So things has become now come to a level of maturity after OCO2 and GOSAT, and they could see the various variations across the globe. I was showing you about the particular example of Los Angeles. And we also were analyzing from CMAK. I had some experience of seeing the CO2 variations, and these are some of the variations of CO2 over India. Obviously, many places over vegetated regions you see slightly less CO2 because of the photosynthesis and absorption. So this is one example how CO2 varies. And yeah, I try to see that the variations, so there are 10 to 20 ppm variations happening in this particular situation. And the dips wherever takes place is all because many a time, of course, it's all because of the global circulation as well as the local photosynthesis happening there. We could analyze the patterns of CO2 increasing, we call killing curves of India, and then many other workers have started. Now the subject has grown to a quite good maturity, and we observed that around 2 ppm per year, the CO2 is increasing. But recently I read a literature from NRSC by ground measurement that is around 2.6 or so. So these numbers are changing and increasing with the time. Once we try to analyze that what happens over of CO2 concentration, and we found that it has an inverse relationship with the photosynthesis activity in our India. Whenever the plant grows, CO2 decreases, and it also is correct for the global observations. We also analyzed some time back the methane concentration using CMAK. Here you can see that it has a regional pattern. But most important pattern, you can see that ultimately it is the Indo-Gangetic plain where rice and those, wherever rice areas are more, you see to them that it is a enhanced pattern there. And it's well known and understood that different regions, West Bengal, Himalaya, and other things, we analyze the pictures, and the variation shows about the major contribution from rice. This was the first observation I was talking about the infrared sounder from NOAA. They could see that whole globe of CO2 from that particular measurement. And when you see the whole globe with this measurement, what you see is seasonal patterns, which has a latitudinal variation. And the latitudinal variation talks about the seasonality, and depending on the vegetation and those amounts, seasonality do vary. So this was some observation. Quickly, I'm going through some observations of CO over India. I analyzed from the MOPIT instrument long back. It was 2.2, 2.6 time frame. Of course, now there must be much better observation available. Yeah, once while analyzing the CO2, the CO concentration in Bay of Bengal, Arabian Sea, I found some Bay of Bengal was showing some uniquely high number. And then while running the transport model, we could see that it is not only the place where this emission takes place, even it is transport from the various places also influence a particular. So while analyzing the what you call the trace gases, one has to be careful seeing the long-term transport and the local inventories to properly analyze, and the chemistry element of it to properly what you call interpret the data. I will quickly summarize that a lot of observations over India was analyzed using this Tropomi CMI, this Sentinel 5P, and this one example done by Dr. Mehul Pandya from SAC, that before the COVID period, it was this kind of pattern. Many power plants were showing huge number. Suddenly, due to the lot of restrictions, power plant continues to have high numbers because they were allowed, but many regions the number decreased. Such observation has seen by various authors in country, but overall it proves that the technology has matured enough to detect the environmental condition and those small variations in the compositions. So that way, Tropomi is doing a very good job, and those of you interested in this kind of application should analyze those patterns. Of course, when you do anything, you have to validate your things. Any researcher has to see that surface measurements and aircraft measurements are equally important. For that, in future there are plans to have a geostationary mission concepts, that instead of polar orbiting, we can have observations of hourly basis. And this concept has been not only conceptualized, it has been implemented in few countries. And in future, there are many such missions, geostationary mission is going to take place because the technology has matured to a good level. And in the last, I would like to just say that this application spectroscopy particularly helps in knowing greenhouse gases precisely. This is advanced remote sensing at moment because it requires a very sophisticated demonstration, very complex modeling to come out with a solution. But at the same time, many good developments has taken place, and now data sets are available to people. Further development, these instruments are required and being done, and ISRO, as well as many places in the world, not only for Earth application, even this kind of modeling of chemistry and that transport is also equally important when we have to understand the other planets in solar system. There are many planets like Saturn and Jupiter has those gaseous environment, and this is technology which will provide the required information to understand the various processes on Earth as well as planetary system. Thank you very much.